Hello everyone, thanks for joining us after this lunch. Today we're going to talk about advanced retrieval augmented generation with some advanced techniques. So is it really going to be the definitive guide? I don't know, because it's a topic with lots of research, lots of new ideas, etc., and algorithms and techniques that like every week there's something new. Yeah. So we're here to talk to you about some of those techniques. And my name is Guillaume Laforge. I work for Google Cloud. So you may know me for working at Google or having created the Groovy programming language. I'm also a member of the Cast Coder podcast for those who listen to French podcasts. I'm a Java champion. And I'm also a contributor and even a committer on LangChain4j.
Thank you, Guillaume. And I'm Cédrick Lunven. I'm a software engineer at DataStax. I also created my own framework, FF4J, 11 years ago. Developer advocate at DataStax, building a kind of tool, CLI plugin connectivity. I also have my own AI startup. So things I will talk about today are partly implemented in production with good bards, so real feedback. Part of the AI product, and I'm also a contributor to LangChain4j.
Speaking of which, we have books to give away, a brand new book by our friend Antonio. We'll tell you more about this later on.
So expect some questions.
Yes. So we have 3 hours, but there's so much to talk about. So we'll do a general introduction just to get everybody up to speed and on the same level. We'll introduce you to a first naive RAG approach. We'll be using LangChain4j for all our examples, actually. And then we'll dive into the more advanced examples. So there are different phases. When you do RAGs, there's the ingestion phase. So there are techniques that you can apply there, but we'll do a little break then, in this area at least. And then there's the querying, the retrieval part, and there are other tricks and techniques that we can apply there to improve the quality of the results that are returned by your searches. We'll talk about, I think we forgot to update this one because we're going to speak about things like Agentic RAG as well, some more advanced techniques, and then evaluation, security, data lifecycle, etc. All the examples of code that you will see in this presentation are available on GitHub. So I show this QR code, but at the end you'll see the QR code again if you want to have a look. So all the examples are there, and we'll put an updated version of the slides there as well. I think we haven't yet. PDF file with all the details. So let's start with an introduction. So large language models, now everybody is familiar with that. We've seen lots of evolution there with bigger and bigger models trained on lots of tokens of text, etc., and larger models with more neurons. Or even there's a trend toward making quantized versions, smaller versions that are as powerful as well. What are large language models? They are a black box inside of which there's a big neural network. The kind of neural network, its architecture is the transformer architecture. That's the name of it. It was popularized more than this, 2017, so 6 or 7 years ago. It was some Google researchers who wrote this paper, Attention is All You Need. And then it was very much popularized by the arrival of ChatGPT roughly 2 years ago. But large language models are big black boxes within which there's a huge neural network with a special architecture. And they are great at generating stuff. So it's not just recognizing patterns, etc., but it's also able to generate text, and it understands the human language and the various languages that we speak very well. Just to give some vocabulary, we often speak about parameters and tokens. So tokens, that's words or sub-words that are used and that the models know about. And when we say, okay, it's a model trained on 3.6 trillions of tokens, that's the number of quasi words on which the model has been trained. So it's more than you can read in your entire life. And the number of parameters, when you hear about the size of a network, it's actually all the connections between the various layers of neurons. That's the number of those connections and the weights associated with those connections. We often say that LLMs are statistical or stochastic parrots, in the sense that they really learn about, throughout the training, they learn about the statistical relationships between words, sentences, etc. And so that's how it learns how the language is made and how ideas evolve through a document and how words are related to each other, etc. There's something we won't cover today, but it's also part of some of the techniques we could apply to improve RAG as well, which is fine-tuning. So you can take an existing model, we'll mention it, but briefly. We can fine-tune it on your own data, your own data sets, to make them more knowledgeable about a particular field. For example, if you're working in a law sector or financial sector or medicine, scientific stuff, maybe if you fine-tune a model to better understand the key, the keywords, the acronyms of your domain, it can further help delivering good answers. Lots of generative AI use cases in 2024. So lots of cases related to language, to help you write, to help you summarize documents, to help you classify texts. That's an important task. For ideation, if you want to, I want to write an article about something, it can help you find ideas or find something you hadn't thought about. Sentiment analysis, etc. Data extraction, I love this use case as well, because nowadays I think we say that 80% of the data is unstructured. So text, PDF files, etc., all the stuff that's on the internet. But LLMs are great at extracting structured data out of unstructured data, out of text. That's pretty cool. And then there's a classical use case, which is a chatbot or search, semantic search. Code, it's great for code. So I use Gemini Code Assist in my IDE. I'm using IntelliJ IDEA. So you can use Copilot and other similar tools. And it's pretty good at code generation, completion, etc. Speech, we're not talking about speech today. We're focusing on language.
No, it's good enough.
But the models have greatly evolved as well to do live transcription and translation, etc. It's quite crazy how it evolved as well. And vision is important, I would say. For example, when you have documents like PDF files, maybe recognizing like the flow of the text or the images embedded into such documents. Vision models are very useful in that case.
Yeah, so today we'll talk a lot about Retrieval Augmented Generation. That's also applied to both speech and vision. So sometimes you don't realize you only apply that to text, but actually you can translate speech and vision into embeddings, and we will show that later.
Right. So I work for Google, so I'll just mention this slide about the what we have on Google Cloud. We'll be using mostly the Gemini model, which is available on Google Cloud in the Vertex AI suite of products. So Vertex AI contains all the AI stuff basically on Google Cloud. I'm just mentioning Imagine, also a great image generation model. And what's cool as well is at the bottom here, you've got Vertex AI Model Garden. And you'll find other models like Llama 3.2, like Claude, etc., that you can run directly on the Google Cloud platform. So it's not just tied to Gemini, but you can also use big models and also smaller models because we have access to all the models available on Hugging Face. Yes. So it's just like find the model, click deploy, and you can use them. And well, all the infrastructure to run on the GPUs, etc. So a key thing we've, I think, all learned about when we started to use things like ChatGPT, the Gemini web app, etc., is that writing effective prompts is important. And okay, you may have a simple question, but maybe if you add more context to that question, then what is going to be generated by the LLM is going to be better, right? So the context, you can feed or explain to the model that, hey, you're an assistant targeting Java developers. So now it knows that we're going to ask something about, developing a class or implementing an algorithm in Java. Sorry. Your mission is to provide helpful answers. I'm not sure if we would say your helpful is not to provide or to provide unhelpful answers, but that helps. You should. So there are some constraints like write succinctly or write in a certain style. For example, something I noticed when using Gemini Code Assist, for example, was that I forget what it was. Read all the lines of a file. It wasn't using files, read lines. It was using like a classical approach with buffered readers. So sometimes adding extra constraints like use lambda expressions or use some framework or something, sometimes it helps the model tailor the response to your needs.
I think it's even stronger than that. In the constraint, you really need to tell if you don't know, say you don't know.
Oh yeah.
Even some big
to avoid
retail
hallucinations.
Exactly, and also even some big retailers right now. If you go to .com and use the bot and ask what will be the weather, in tomorrow in France, that thing will actually reply instead of telling you, I should just focus on the mission you assigned to me and try to answer everything. So constraint is also for you to protect yourself against what the chatbot or the AI you provide to your customer could do, because you are accountable for that AI. So we heard about that airlines company where the customer were able to, purchase a ticket on a plane that was not existing, and so of course the company has to.
Well, there was a guy who managed to buy a car via a chat box for $1.
Yes, exactly.
Wow.
So constraint is not that just.
But as we will see for RAG as well, it's important just to say, hey, base your answers on the content that we provide, not your own knowledge. And then you can also give some samples, some examples. So that's the techniques like few shots, prompting, etc., to guide the model into following a certain format or better understand the task beyond just the explanation of what it has to do.
Also, make sure to format your prompt template. So the LLM is actually quite familiar with that structure. So if you use Markdown and introduce each part with its title, really make things obvious, you will get way more better result.
Yep. So those LLMs, there are a few knobs that you can tweak to give different answers, like more factual, more creative. So one knob that you can turn is the temperature. So the temperature, usually between 0 and 1 or 0 and 2, depending on the models. When you use a lower temperature, it tends to be more factual, more deterministic in what it generates. If you have a task which is more creative, you'd better use a higher temperature, because it's going to find words or tokens that are less likely to be used. You have the top P. So top P, as we say, those machines are there to predict the next word. But there are different words that can come up after your current sentence. So, well, I don't know what was the sentence there, but should the next word be Java, IA, Langchain, Spring, etc.? But there are probabilities associated with those. So it's more likely, like half of the chance we have, it's going to be Java. That's going to be the token that is selected at random. But we can say, okay, I want the cumulative probability, so that's the top P parameter. So you say, okay, I want that the next token be chosen among those tokens whose cumulative probability is up to, or at least 0.8. So here, 0.51 plus 0.53 plus 0.11, then we're beyond 0.8, the top p-value. So it means we'll only use those 3 tokens will pick one at random from those ones, not from all the possible other tokens. Top K is a little bit different. We say, okay, we choose up to two. We're going to choose at random between two tokens. More and more, I think models tend to use top P rather than top K because it gives a better set of, or let's say, richer answers usually than top K. And the last one, you can also decide how much token you want to generate. With more tokens, okay, maybe you're going to have a more detailed, a more in-depth answer. But then there are also cons, which is the fact that, for example, costs, the more you generate, because usually you pay per token in input, but also in output. So there are pros and cons, and sometimes for longer answers, you may have lower precision or sometimes some repetitions, although models are not over-repeating too much nowadays, but things like non-instruction tuned models are really creative and very repetitive when you play with them.
Especially if you put the temperature higher.
Yeah.
So temperature higher means more creativity, but there is no one value better than the other. It's very based on the use case. If you want to generate an article, maybe put the creativity a bit higher. If you want to do like summarization, get it lower, just less imaginative.
So LLMs are great. However, there are also some limitations. So the first limitation I'm going to mention is the training cutoff date, which means that, well, the model was trained on a huge corpus of data and text and so on, but the training stopped at some point. So if you have, let's say, the model was trained on like news from August, then if I ask a question about stuff that happened last week or today, it doesn't know about those things. So if you want to have information that is like super fresh, well, you won't get that out of an LLM because it's got a cutoff date. And of course, it doesn't know about your data. And I think it's actually a good thing that it doesn't know too much about your data, because often your data is private, is personal, is, it's your company, it's your customers' data. So you don't want that data to leak. That said, you want to do something about that data, and some smart actions about that data. So how can you expose such information to the LLM when you needed to think about that data? So, okay, you could put that in the large context window, but there are limits to context windows as well. LLMs are not necessarily tuned for, let's say, your use case, etc. So maybe they are harder to steer in the direction you want them to go. So you've got a specific task in mind. Maybe in spite of good prompt engineering, maybe it's not going to follow what you really wanted to do. Hallucinations, very important topic. So the more you prompt it correctly, the less likely you're going to get hallucinations. But when you ask questions about your own data that the LLM hasn't seen, you have to ensure that, okay, base your answers on my data, the one that I feed you. Don't invent something. And if you don't know, just say, I don't know. What else? Yeah, work with limited input to context windows, because there's a limit to what you can send an LLM in terms of size. However, there are models
not so true
which
anymore.
accept huge context windows. So I'll mention Gemini, which has a context window of 2 million tokens, which is just huge. So you could put, I think, like the whole of Harry Potter and Lord of the Ring in the context window, which is crazy, which is insane. However, the generation, the output generation is also linear, depending on the amount of tokens you send, and the cost is also linear. So if you want to trace the the trajectory of one character, from Harry Potter or Lord of the Ring, it can do that. But it's going to cost you a lot. And I wanted to show you a little example there of, I think I have it there. Let's put it in a big screen. So something where at which LLMs are, especially the big ones, are good at is really making sense of the data rather than just finding the data. It's good at thinking and deduction, etc. So for example, if I give, so upload to drive, and I need to find my file. I'm going to give, I think it's named EA, where is it? This one. I think I had the, let's try with the PDF. I think I had the, all right, I'm gonna do Apollo mission. Where is it? Well, never mind. I'll take the PDF. Let's see if it works well. So I have the PDF of the whole transcription of the Apollo 11 mission. And if you want to do a RAG on something like this, so you'd have to split that text into small pieces. But there are some kind of questions where RAG, we'll see, can struggle. For example, if you ask something like, at which time code in the Apollo 11 mission did Neil Armstrong say his famous quote? And the thing with that, so I have this, so you can see already the number of tokens, that's 500,000 tokens. And doing something like this isn't easy, because if you search for Neil Armstrong in the document, it's mentioned, well, I didn't show you the document, but it's mentioned at the very top, but throughout the transcript, it's not mentioned. So the model has to figure out which line is said by which person. Then it also has to figure out that famous quote. If you search with RAG, famous quote, it won't find the famous quote. What is the famous quote that he said? You know?
You can, yeah.
Small step for, etc.
We'll find it.
Yeah. And let's see. And this is a task which is quite hard. So let's see. Neil Armstrong said, "Okay, one small step at." So I trust it. I don't. I won't open the document, but at 4 days, 6, and at least that's the right format for the time code. 4 days, 6 hours, 45 minutes, etc. So it's quite good at understanding text. But as you can see, it took 45 seconds, which is big. That's if you want to do a chat with the Apollo transcript. Maybe RAG will be better because it does much faster searches.
Yes. So here you put a document, and still it's not RAG. You ask question to your document, but it's still not RAG. Here is simply that we put the whole document part of the prompt. We are still doing prompt engineering, nothing else for now.
Yeah. And when I did my screenshot, I used the HTML page, and it was faster with the HTML page, maybe because of the PDF parsing or something. I don't know. Okay, and just to recap, 2 million tokens, that's like 2 hours of videos with the audio, with the images, etc. 22 hours of audio, so you can give it a podcast, tons of podcasts. 60,000 lines of code, or 1.4 million words, which is pretty huge.
Anyway.
So let's talk about Retrieval Augmented Generation. You remember this schema from earlier. The key thing here, I would say, is that in addition to the other aspects, we have this new section, document sources, your relevant document extract. We will search a database, a vector database, to find the relevant information, and we'll put just those extracts. We won't put the whole Apollo 11 mission transcript. We'll just put parts we're interested in. And in things like constraints, like you mentioned, so you'd better say, just use the information given below and not try to invent something. Okay?
The key part here is really extract. When you put your PDF, you were simply putting more context in the query before.
Throughout these examples that you will see in a short moment, we'll use LangChain4j. Maybe you wanted to speak about it?
LangChain4j is, I think now, the top leading library in Java ecosystem to build generative AI application. The other one is Spring AI, obviously, but not so many not so much success yet or traction yet. So in such application, what you want to do is simply interact executing such models. So it started with the chat language model, but more are coming with image model. We have a demo right away. Embeddings, that's about the RAG. We will go deep into those. Scoring model for ranking, re-ranking, and moderation, and more are coming. Text-to-speech, text-to-video, moderation, summarization, all those models. So in Java, we were not really executing those models. We were not doing inference with those models. We will simply connect with technologies that expose those models for us through APIs. So this framework has been created like 1 year ago, 18 months ago at most. It's already integrated with all those technology. But it's really recently, thanks to a project called GLAMA, that some of the model can actually be executed in Java. The Onyx, the Onyx format, which is a way to represent a model, has been around as well for a little bit more time, but model were quite
and can even run on CPU.
Small, yeah. So
for embedding models, for example.
Yeah, we're getting to be able to execute model in Java, but we are not as advanced as our friends.
And there's a talk about
Python.
GLAMA. Is it today? I forget. Later today?
Yeah,
or the
I
next
think it's
day?
tomorrow.
Oh, maybe tomorrow. Okay.
Yeah, exactly on that. So disclaimer, we are pushing long-chain 4J quite a lot during this presentation. So sometimes we're not so nice with it, but we still love it. Also regarding the name, it's called long-chain 4J. Obviously, there is a reference to long-chain in the Python world, leading by Arish and Shays. Those guys are totally aware that the long-chain 4J project is using the name. They are totally fine with that, but it's not associated with that. There is no relationship really with the
name and inspiration, but that's pretty much it.
Yeah, so eventually that project will change name in the future.
Yeah, who knows? We'll see.
Okay, so with that, it's almost 5K stars on GitHub already.
Yeah,
so pretty good.
That's nice.
Maybe before going to RAG, you want to do a little demo of what can Gemini do with just language model?
I forget which one we wanted to show.
10, 11, 12.
10, 11, 12. Right. So let's have a look at
so maybe
10.
You can. Yeah. So this is the list of samples we have for you. So it's like probably 40 samples.
So when you use long-chain 4J, there are lots of builders to create chat language model. Chat language model is an interface. So all those builders here, we're using Vertex AI Gemini, but all implement that interface. And then to ask a question, this is here, chat model generate, and you can pass a user message or a string. There are different signatures, and it's going to print the response. So it's fairly. I guess I'm gonna run that with the big one, and that way I'll show you all of them. So, for example, the first one is about generating a poem about DevOps. Oh yeah, it goes a bit too fast for me.
Even with the typo, it's working good.
Oh yeah. So in Antwerp's heart, blah blah blah, take key and furls, whatnot. So which one is it? It's this. No, that's this one, the poem. So this one, it was. I forgot to mention that we have usually two flavors for a model: a streaming model and non-streaming model. So we tend to use the chat model usually rather than the streaming. But streaming, you can see the tokens appear progressively. So that's what you saw with the here the output of the poem that was output pieces by pieces. So the simple question was this one. So why is the sky blue?
Wow.
We have some typos to fix.
Yeah.
Okay. But as you can see, it's fairly easy to do, and the code was pretty trivial. That was the first one I was showing here.
Yes.
So generate the user message, and let's print the response. So this other one, the one that showed like what are profiles of DevOps attendees, you notice that we tuned, or we tweak the parameters of the model by specifying like a different temperature, different top P, top K, or things like the number of retries it should try till maybe you exceed your quota or something like this. And the maximum, it doesn't mean that it should output 2,000 tokens, but there's a maximum of tokens that it's allowed to generate. So it's fairly trivial to call a chat model.
So the chat model is interface, and there are one builder for each technology, for each provider of those models. Let
me show you an image model, because you can also generate emails. So we've got the blue sky. Maybe we don't have the beach here in Antwerp.
Yeah. And if you check the code, is really similar. A builder,
lots of parameters.
I'm
using the Imagine 3 model. And then the question is, hey, I want a photo of a sunset over Malibu Beach. And then let's see, so it generated 3 pictures. Oh, yeah, it's a bit small. 3 pictures, and it looks pretty much like a possible Malibu Beach.
It's as simple as that to use an image model.
Exactly. So. And all the models, so if you want to use other models like DAL-E, etc.,
there is DAL-E, Stable Diffusion already in Midjourney
the same interface. And I think this one, prompt engineering.
Yes, so here you see that the prompt is actually formatted with the directive, the constraint, the user question using Markdown.
Very structured.
Great practice. And it's a template. So in the template, you saw some keys that you want to replace. Think about Velocity Engine for others among you. And Mustache, you just replace the template.
We replace the placeholders. And same thing, generate. And I'll show you the other one. But there are also here system prompt and user prompt, because you can also, there are some prompts that are different, that are more special. The system prompt is such a special prompt, because it's usually you put the instructions that can be overridden by the user as a system instruction or a system prompt. So here in that example, we prepare like the instructions, but then the actual query from the user is as a user message. And then when we do generate, we create a system message from that prompt, and we create a user prompt for it. And then, you can see, I won't read everything, but that's the idea.
Yeah, I think that's good.
Yep. Naive RAG. Okay, so let me explain, or a little refresher about how RAG works. Retrieval Augmented Generation. There are 2 phases. There's the ingestion phase, and then there's the retrieval or querying phase. How it works. First of all, you have documents. You're going to cut those documents into pieces called chunks. And for each of those chunks, so not necessarily tokens, but like sentences, paragraphs, etc. For each of those extracts, those chunks, you're going to calculate vector embeddings. Vector embeddings, that's a big vector, high dimensionality, like 768 floating point numbers, which represents the semantics, the semantical meaning of the chunk. We are going to store in a special database, we're going to store the vector plus the chunk of text, okay? So the vector database, so not all databases are vector databases, but there are more and more databases that add vector support. That's the ingestion phase. Then you've got a user that comes with a question. So this is the prompt there. The prompt is going to follow the same embedding calculation. And we'll have a vector embedding that corresponds to the prompt. And what's interesting with those vectors, those semantic vectors, is that a query vector is going to be similar to a vector that contains the answer to that question, because semantically they are linked, the question and the answer. So if you search the vector database for similar vectors, it's likely that the answer is going to be available in the chunks associated with the most similar vectors that are found in the vector database. And the whole point then of RAG is this part where you create a special prompt that says, okay, here's the context, you're an expert in whatever. Here's the question from the user, and base your answer on the retrieved documents, the retrieved vector and their associated text. And really base your answer on that. If you don't know, you say you don't know, okay? And then the LLM is going to generate an answer, and through your chatbot app is going to send the answer back to the user. So that's, the naive and simple architecture for RAG. However, there are problems that may arise. For example, how do you load and parse the documents? Fortunately, Langchain4j has got components that help you with that task. But then we said, we're going to split the text of the documents into chunks, but how big should they be? How small should they be? If they are too small, maybe some sentences may be cut into pieces so you don't have the whole context. If it's too big, the semantic meaning may be diluted because we cover several aspects in the same paragraph, for example. So what's the right size for a chunk? And it's not easy. Next, is the context relevant? Meaning that, okay, perhaps you have a quite small chunk, but maybe the LLM would be able to give a better answer if it knew more about that chunk, where it came from, what were the sentences before and after. Maybe it's important to generate a good response. Did we embed and store all the info? So that's also important because you may have some missing information or stuff that wasn't chunked properly or something. There may be different reasons for that. Is the question close to the answer? So I said, question, answers, they should have vectors that are similar. But maybe we'll have a look at some techniques to see how to improve that, because maybe a question is not that close to an answer. And maybe a question is closer to a question, or an answer is closer to an answer, but we ask questions.
Sure.
We'll see. We have some ideas for that. Did the LM really include the answer? Because it's a generation issue. Maybe it had all the information, but for some reason, the real answer was not part of the text it generated. So maybe some prompt engineering issue or something.
Yeah, that's what we call the precision.
Yeah. So let's have a look at
the naive RAG. So let me run it like that and then explain. So here, that's our starting point. I just hide that. Maybe go into here. So ingestion. So you see we get the file wherever it is. We parse the file, get the input stream, load that as a document. This document is then split into pieces and saved into a store, which is the embedding store. Okay, and to get those pieces and splits, we are using an ingester. So the ingester will take the document, split the document in a way. So we will different splitter. We will explain a bit of that. Use the embedding model, which is the LLM, to transform each chunk into a vector and save that in the store. So that's what you call ingest. And all these steps, it's so easy to do with these Langchain4j classes that just glue all things together. We simply have to declare each piece one after the other. Okay. So you ingest the document, and then you retrieve the document manually. So here I'm still asking.
We're using the low-level components.
Yeah, the low level. So here I'm using the store. This is where now my document is saved. This is my embedding model where I actually use to encode my question. I'm building a request, which is find me, who is Johnny. So what I embed is a text file. So how do I get out here? So I you used a text file, which is local over here, discussing about a race hole called Johnny. And this my naive RAG will simply ask who is Johnny. So it will look at the store, take the question, encode the question, compare the question to my store, and give you a result. So here it's still fairly low level. I need to create my query. I need to populate my RAG context. So I have my, okay, it's a lot of, let me go back to my code. So here I have my prompt. You need to answer the question based on this context. I need to encode the question, I need to encode the context, and I'm finally asking the chat language model to answer that question based on the context substitute by myself. Okay, that's still quite some work, right? Well, Langchain4j, again,
simplify this further.
When you are using naive RAG,
yeah, especially for naive RAG,
yes, give you that 10 line of code to do the same thing. Like here now you have the content retriever, so he's aware of the store, where are my vector, he's aware of the embeddings, so with that he can totally encode your question, find the RAG context. And I'm using an assistant that is actually simply an interface here to decorate this interface and give you the result right away. And yep, you got the response. So here it has been executed. Here I got my different chunk embeddings, and he will get you the result. So here we conclude that Johnny is a renowned international racehorse story transcends the sport itself. So it's very quickly naive RAG, and I'm going so fast because in each component we will now dig and see what's can go wrong and how we can push further.
Mm-hmm.
All right, that was for the naive.
Yep. So, or no, is it you?
I think,
it's still you, actually.
Yeah, I'm keep going.
Keep going.
All right, so in
Race
the naive RAG, quickly we saw the loader, the parser, and the transformer. Because what we want to get at first is a document. So that document gets the text of, the text what you try to retrieve. Could be different format, PDF, text, doc, different. But you also have the metadata. And the metadata is really not to be forgotten because there you find the file name, the file format, the source, and all those information at the end will still be in the store, in the database where you get your embeddings, and that will be useful later when you search for them. Okay, so what are those? Well, once the document is there, it will be splitted. We saw the recursive, a bit naive splitter, and you will get segments. So segments are chunk. In a segment, you have the chunk, which is the text, and you also have metadata. And then we transform that segment into the embedding model to get this embedding, which is our vector. And part 3 of the ingestion model is you have your segment, you have your embeddings, and you will finally save that into a store. Okay, so in Langchain4j, what do you have? Right, loader, parser, transformer. Loader, you can load from file system, from URL, from S3, cloud storage, blob storage, GCS, GitHub, Tencent, Selenium. Okay, so you have different sources, and actually some companies are just like vectorize.io are just creating some tools to get you the data out of those. Okay, so you extract the input stream from your files. You also know what is the format of those files based on the source. Then using some good old Java framework that we all know here, like POI, TK, to extract the data from Office documents, doc,
PDF
XLS,
files.
PDF, and PDF box to extract from PDF. Different PDF extractor exists, but in Longchain 4j, as of now, it's PDF box. And when you read from a website, you also need to remove all the tags, and you do that with gsoup. And in the end,
the HTML document.
For the HTML document, yes. So and you end up with that document. And when it's there, it's still not finished because the text, most of the time, you need to make sure the encoding is okay. You need to escape special characters. Maybe you need to remove some blank line stream. So even if that document ingestion, you still need the data cleansing phase of those machine learning type of project.
At least the components do a good job and cover most of those aspects. But you can also create your own document loaders and from your own sources, from your own locations, as long as you provide an input stream.
Actually, yes, for you today we created two, which is
we'll
GitHub and a Hugging Face dataset. Okay, so speaking of those loader and parser, now I get used to how it works.
Yeah.
Okay, so here going back into the loader and parser. Let me hide these. So here I will, and hide that. Okay. In the different source code you will see, we created some utility methods. So here parse file system, where depending on the extension of the file, I will say it's a text file, it's a PDF file. So you still need to know which parser to use. That's your job. It's not only with the input stream that the framework will know. So you get that select parser. Once you know which parser it is, you get the input stream and you load using here file system loader. The others loader provided in Longchain 4j are URL loader. That okay. So here, three different type of document parse. One using the So here one using the text parser, one using the PDF parser, one using the Apache POE parser. Also, what we want to give you at the end of the session is all those standalone working unit tests to address each part of the framework. So here, if I want to load a URL, I think it's still going on. Here I will get the output of these the DevOps conference. So here you see the output of these should parse a URL. And here two little custom made. So the first is extract a file available on GitHub, which is actually our presentation. And another one from Hugging Face. So if you are using Python, always frustrated me, you just have to do in notebooks, load dataset, and it's doing its magic, just downloading everything from Hugging Face. So here you go. You will have the same type of behavior where just provide the repo, the account, the repo, and the file, and it's loading the document. Okay, that's loader and parser. You saw different formats and different source available, and you can create your custom source. All right. Okay. Now let's move into vector. So you get your data, you load your data. The objective is really to transform those data into vectors. So I don't know about you, but in my studies I did a lot of mathematics, and when I finally ended in a software engineering school, it was a bit of frustration that all the nice mathematics I learned at school was not able to use it in my day-to-day life, and this machine learning thing is quite good to put it back into math. Yeah, in the math what do. So a vector, if you remind, they're not a phenomenon with a direction and a length. So here I put the vector as the origin. So you see x, o, y, o, and the vector is the length. A vector has components, okay, and is defined in a space with a dimensionality d. Okay, a vector has a norm, which is the length of the vector, okay, And here you got a formula to compute the L2 norm, which is the square root of the sum of the component put at square, L2. Okay? The different vector in a space is called a vector space, okay, with the same dimensionality. Okay, that's vector. Now, what about what we are doing? Well, we do have here our question or chunk, and we will transform that question into a vector with components. So the components here are called embeddings, and we still have a dimensionality. So when we work with some vectorization or embeddings, we do have an embedding model, and an embedding model has a dimensionality. And you need to be aware that right at the beginning. Because if you define something in a vector store, you need to know that dimensionality in advance. That's something you have to know. Okay. So vector, space, and dimension. Vector space is flat, so you can add and do some arithmetical operation on vector. Very important when it comes to working with your model. Here you saw some model. I mean, some spaces when the dimensionality is 1. Is there really a vector? You are on the line, just the norm should be enough. You don't really have any direction. On the flat plane, so you just have your vector navigating on the plane. And in 3D, you have the space around you. Okay. But what about higher dimension? Yeah, more than 3. So what if I ask you, show me a vector on a space of 768 dimension? So this is what it could look like, right? So yeah, you really got a hard time showing that type of vector. And still, this is where the vectors are living on. So just a question for you. In 3-dimension space where we live, we call the unit vector of norm 1. Do you know how do we call the vector space representation of all the unit vector in 3-dimensional space? I mean, maybe we need to make it faster. Yeah, kind of. Yeah, okay. That's the unit sphere. That's the vector space of all the vector of norm 1 in a 3D environment. That's super important because most of the embedding model you will use, you got some very long vector, and if you already use them, it's full of 0 and very, very small number. Do you know why? Because those are normalized vector. The norm of the vector is 1. And there is a good reason for that. Because if the norm of the vector is 1, the computation of the similarity in between vector is way simpler. There is less calcul to be done. So speaking of similarities, how can you measure how two vectors are close to each other? So close is really some kind of word you don't want to use. Similar one to each other. Well, we already know, for a very long time, the L2 distance this time. How do we compute a distance in between two vectors? Here we are doing the difference, put that square to the sum square root. That's very the Cartesian definition of the distance in between two vectors. But here you can see that the more is the distance, the less similar are the vectors. So using the L2 distance, it's not a great thing to say if two vectors are similar or not. And the cosine similarity that are most used in AI model is a scalar product of the vector divided by the product of the two norms. So here you have the formula moving quicker. But so when you want to compare vectors, you can pick one or another, or even a third one, which is called dot product, which actually is the sum of the product of the components. Okay. So now that you know what is a vector space, and a few formula, and you know that we transform the sentence in vector, how do you know which vector is close to another? Well, it's your choice. You can pick the Euclidean similarity, you can put the cosine similarity, or you can choose the dot product similarity. And depending on your use case, you will pick one or another. And so the distance is different from the similarity, and you can pick the similarity you want. So
more
formula. But I do that in the beginning, and but I still want them to come back after the break, so I will try to make it fast. So here, simply put, so the different formula for different similarities based on what you want to do. But the cosine similarity is one database, can be different from the cosine similarity is another database. We have the choice as people who are building database to do some rescaling of the similarity if we want. So here, that's just simply rescaling just the definition. Okay, so why I'm telling you those is when you will start working with those embeddings, and you will have to pick for a similarity. And based on the use case, you want to switch one to another. So if the vectors are normalized, which is now most of the case, you want to try to use dot product, because the dot product formula is faster.
You don't have to divide by the product of the norm.
Exactly, because it's one, right? And so, you will really be faster just by changing the similarity to dot product if you know that your vectors are normalized.
And it's important to be faster, because for your searches will be faster if you chose the right formula.
Sure, and still everybody is using cosine. Have you run some tutorial? Everybody does cosine. Why? Because when you do a tutorial, you don't really know what type of vector you will get from out of your embedding model.
Are they normalized
and if you do cosine model, it's working all the time. If you do dot product, you will have weird result if the vector is not normalized. But still, there is a value. Sometimes the length of the norm code for like a weight that you should use it more than another. So my recommendation, if you know that your vectors are normalized, dot product. If you don't know, cosine. And very in few cases, Euclidean. But to be honest, barely using it. It's the definition, right? L2 similarity, that's where you start.
But it's important to say that similarity is different from relevance. It's not because two vectors are actually similar that they are necessarily as relevant to each other. And we'll see later on some demos where we sort the results by similarity, but it's not actually the most similar vector that, for example, contains the significant or relevant response to a user query. So it's important to keep that in mind, and that's why we'll also use ranking or re-ranking APIs to reorder the right values.
Yeah, that's coming. So here is sample vector search, also called similarity search. Your query vector is the purple line. And here, using this time Euclidean distance or Euclidean similarity, that just is good for the purpose of representation. You are building some circle, and you see the first hit, the second hit, the third hit, and this is how you get
I thought that was the first sheet, but no. There's
a
space, right?
Yeah,
okay.
That's you, yeah.
That's my tokenization that's got some issues, I guess.
Yeah, there is even a T. I don't even know why you think that. Okay, so vector search, transform into embeddings vector, and then compare your vector to the existing vector in the database to get you the chunk that are the more similar to what you're looking for, your question. Are you really embedding just a question? We will know with you. Maybe we can do better. And so before going into chunking, let me run this time a few demo on vectors. Again, for the purpose of giving you that after the session. So here we do have, here it's computing the L2 norm. And here you see,
We've got big vectors.
yeah, big, it's coming. Okay, all right. So here it's our big vectors that we get. Okay, so here I'm using a first model. So the model is from Gemini, and so the dimensionality is 768. And here is one of the models that you can actually run locally
on your machine,
because it's an Onyx file, and you can actually run the inference on your machine. And there is a good reason for that, because it's a model that is quantized, and we will see later on what
fast.
actually does it mean. It's fast and smaller.
Yes.
And so here you see vector dimension and the norm. And actually, if I can show that both norm are 1.
Yeah, but yeah, we've got big arrays. So
yeah, okay.
So with rounding errors or rounding calculation, we saw at the very bottom you saw 0.9999.
Yeah. So here is the norm. Maybe I can run one by one next time. Hopefully your thing is 1.
Yeah, maybe.
So the norm is 1. Okay, and when you compare two vector, here you will compute the L2 distance as sample code. So now what about vector similarities? That's this one is pretty cool. Okay, can I just try to run that?
Yeah, I might need to.
No, okay, I need to run the whole
need
thing.
to set the environment variables for each method. Something that annoys me in IntelliJ, it should like inherit the environment variables.
Okay, so
at different levels.
Yeah. So here you can see, depending on the model you pick, look at that. You don't have the same similarity, even if the inputs are the same. So here, look at that. We are using the default small embedding model, so all mini V2 that everybody using. We do have baby dog, puppy. We are building 2 embeddings. And we are showing the similarity, the 3 different similarities of those 2. And here you can see 0.72, 0.73, yep, you got them. Okay, so. But now if I'm using the embedding, actually multimodal from Vertex AI, this one it's a multimodal.
Multilingual. It's not the multimodal one. Multilingual. That supports more languages.
Yeah, multimodal is French, you are Spanish, supporting whatever. Both text and image actually. Yes. So yeah, multilingual. You will see that actually the similarity, and especially the cosine, which is the default used everywhere, will be better. So here, and that's also part of why the multilingual model is better. You might expect that a baby dog and a puppy are pretty close. And here, if I say, if I can change here jeune chien
in French.
Yep, I will get.
And maybe you should change the other one so that you see
that's what I'm doing right now. Yep, and here you go. So you should get a better result with the second one, because it's aware of the translation of the model. But at the same time...
So yeah, with cosine similarity, it's 0.2, that's super small.
And with the multilingual model, it's way better.
So the key thing to remember is that if you have data that is in different languages, French, English, whatever, you'd better use an appropriate model that understands different languages, right?
True.
So it's important to think about the embedding model that you use in your RAG use cases.
Exactly. And the size of the first one is actually it's smaller.
Yeah.
So for puppy and dog, it was not that bad because you got 0.74. But here to have things that are rather different but similar in another language, the similarity and multilingual was much better. Okay, so now what about chunking? How do I get
big knife? I'm going to cut stuff into pieces, right? So chunking. So here we covered loading, parsing, transforming documents. We were speaking about the embedding, but first you have to get those chunks and split them into small pieces. So there, or you wanted to do that one, or
Oh, that's actually
that,
like before what is available out of the box in LangChain 4j. So what you want to split, which is the second column, you want to try to split by sentence, by characters, or you try to be recursive and try to get something
different levels.
Yeah, with the different level, different paragraphs. And then get your text segment that will be translated into, in the end, the response with the embeddings, which is a vector
of floats.
And some metadata that will actually tell you how the chunking happened and if everything is okay or not. So here we will show you the default chunking. But to be honest, to get more context and more relevant, not similar, relevant, you need to shape your context in a way that the chunking is made better.
Maybe let's look at the basic splitters that are included.
Yeah, the default one.
So, which one is it? Embedding tokenizer.
Chunking defaults.
Chunking defaults, that's this one. So I'm going to run it. Okay. So there. Oops, no, that's the wrong keyword. Shortcut, sorry. So again, we're going to load a document. Okay, and we'll use different splitters. So let's start maybe with this one, by characters. So you can say, oh, okay, I want to split by chunks of 300 characters, and maybe I want some overlap. Maybe I want to include part of the end of the previous chunk to avoid cutting sentences in pieces. You can also split. So all that are default things available in LangChain 4j. You can split by line. A line can contain several sentences, maybe a whole paragraph. You can do by sentence directly. And this one is interesting, recursive. Maybe we can even look at the implementation because it's actually doing a recursive split. So first, it's going to split. Oh yeah, there's also a paragraph. We split by paragraph. If it's still too big, we are going to split by line. If it's still too big, we're going to split by sentence. And if the sentence is too big, we're going to split by words. You get the idea. So that's why we call it recursive. We do different levels of recursion. And so, yeah, we can see here some of the results. So here, that's the whole text. And then we are using the recursive splitter. So because we said, I think, 302 and 20 of overlap or something like this, it looks like it followed pretty much either sentence or lines, because you can see some chunks have got 1 or 2 sentences. Split by characters, well, you see the different ones, so those ones are explicit. Split by sentence, this one is really following the sentence. So for example, let's take this one. You're going to see there's just 1 dot at the end. That's a long sentence here. So you can pick one of those default chunking algorithms, or you can use the recursive one, which is nice because it splits things progressively at different zoom levels until it fits the size you asked for.
Okay, so here, even with those default and sample splitting, we can go too high on the size of the chunk, because that chunk will be encoded as a vector. And as I told before, the vector has a dimensionality, limited dimensionality, 768. So based on that dimension, the chunk should not exceed a certain amount of not token, not characters per token, which is even chunking splitting the chunk in small pieces token. So 300 is kind of the default and where we get the.
Usually I go with 500. I like 500 with like 50 of overlap.
But for the all mini, I stick to
but for
300.
All mini, smaller seem to be better.
Yep. And there is no straightforward.
And it also depends on the density of information. Let's say if you take a book by Proust, the French author, like one sentence can span 3 pages. What's happening in that sentence, I don't know. But sometimes, like technical documentation that we write, etc., or even financial reports, usually the density of information is it's much more packed, right? So smaller chunks might make more sense than bigger chunks. So maybe for books, bigger chunks is good. For more factual data, condensed data, maybe smaller chunks is better. But again, it all depends on your data. So you have to try that. There's no magic value, unfortunately. We're going to study some advanced chunking techniques. So you know Chunk Norris, right? They're
Okay, they awaken now.
you just need a good Chuck Norris joke to get the crowd. Wow.
The more you get, the better are the joke.
I'm not sure. I can't promise anything there. But yeah, so we saw the different boundaries, sentence, line, paragraph, etc. But there are some interesting approaches to that, like hierarchical chunking, etc. So we're going to have a look at some of these. And even some, like this one that I'll show you, contextual retrieval, it's one that is 2 weeks old, right? 2 or 3 weeks old. So it's fairly recent. And even semantic chunking is a few months old. So there are new ideas that come up every weeks, month, etc. So I'll take, as an example, the Wikipedia page about Berlin. Okay, so it's quite a long page. I think I have it open somewhere there. So it talks about like the history, the geography, economy, temperature, energy, etc. So it's a pretty big document. And we have the raw text. So this is just the very first paragraph. So Berlin is the capital, blah, blah, blah. We mentioned the default splitters. So you can say, okay, I want to split by 100 characters chunks. If you look at this, you're going to see splits, sometimes split words, split sentences. And if you look at like this part, okay, the Salmon one, population, and the actual population is in the other chunk. So if you ask a question about what's the population of Berlin, neither chunk has got the answer, right? Another approach maybe would be to use, what do we store in the vector database? We store the chunk, and we store the vector embedding associated with that chunk. No particular metadata. So far, so good. Let's say we're going to use overlaps, bigger chunks, but with some overlap, so that this one goes, the salmon, orange, reddish one, goes up to there. But the following one starts there, so there's an overlap between the two. So it's interesting because this new chunk there has the population of Berlin. So if I search for that information, I likely get it. So you're going to say, yeah, maybe I could do something even bigger. I would have had the answer as well. But you never know where the chunk is going to, the split is going to fall. Here, we still store in the vector database the chunk and the vector. Okay. So chunking defaults, we already saw that. Maybe I actually like splitting by sentences because usually you don't split the meaning across two chunks. Each sentence usually is a unit of meaning in a way. So I like using sentences. But same thing, we store the sentence and the embedding vector of the sentence. But let's see another approach, which is a parent-child approach, where instead of just looking at the actual sentence in darker green, we're going to also look at the overall context. So here, for example, the level, parent-child level, is paragraph, sentence. And why is it interesting? Let's say, again, I ask about the population of Berlin. If I just look at this sentence, population 3.85 million. But the population of what? The subject of sentence is its. I don't know that it's about Berlin. It could be a sentence that is about Tokyo, Antwerp. Don't think there are as many inhabitants in Antwerp.
Who knows?
So what's interesting, when you do the RAG part where you put the data in the context, in the LLM prompt, maybe it would be a good idea to actually give the whole context, the whole paragraph here, because everything, like all the entities will be somewhat related, and the its will correspond to Berlin. The LLM will understand that this sentence that seemed interesting when I did my vector search, when I did the vector similarity, the LLM will figure out, that's the population of Berlin. So it's interesting to give the LLM more information than just the sentence whose embedding matched the query. So we embed the sentence, okay? And we store the sentence, but we also store in the metadata the paragraph, because we'll be able to retrieve that and pass that to the LLM. A similar approach, this one I'm going to show you a demo for this one. It's a same idea, parent-child, but the parent is actually a sliding window of sentences around that sentence. So I decided to say, okay, for that sentence, I want one sentence before and two sentences after. So let's have a look at an example here, an implementation of this. Chunks with wider context.
So here we are using some chunking that are not yet into LangChain Forge.
Oh, yeah.
That has been built for this presentation and more to come.
The document is pretty big. So I have, where is it? So this part, chunk with wider context. Yeah. So I load the document. I split the document in sentences. But the key, no, that's the next one, which is where I'm using the strategy.
But still you build the sliding windows.
So I have a little algorithm that I built myself with, lambdas and streams and so on. I built a sliding window. So let's go back here. I built a sliding window which says, okay, the current sentence plus the previous one plus the next one. I'm going to calculate the vector embeddings. I'm storing that for now. Just there's a small in-memory database, vector database in LangChain Forge. That's nice for tests, at least.
You don't need the metadata, actually. For anything that you don't need metadata and small data set in-memory embeddings, it's good for unit testing.
Exactly. And then I'm going to call the embed all method, and I'm going to embed all the sentences, but store the surrounding context. So how many inhabitants are there in Berlin? That's my question. I'm going to do a search query, max results 4, mean score 0.7. And I'm going to compare the embedding of the query, how many inhabitants are there. And I'm going to show the similarity, the calculation of the similarity, and I'll show the embedded child and the embedded context. Then I'll ask Gemini to say, okay, so you must answer the question. Here's the extract, and instead of putting just the sentence, I'm putting the context, the sliding window of sentences. And I think I ran it. Yeah. So here are all the sentences being split. Quite a lot of sentences. Okay, let's go more. I'll go to the end. Okay, and then the searches start there. So I've got this question, and actually I should have shown without doing this. So if I didn't do this chunking approach, the result I think was 0.880 something. But here, because so you can see that this embedded stuff, that's what I embedded, but this is what I return and I give to the LLM. And indeed, so this one speaks about population but doesn't really contain the answer. But if I give the overall context, actually it's got the answer there. So it's useful because this vector matches well with the query because it speaks about Berlin and population, but it didn't have the answer. However, the surrounding sliding window has the answer and has the number I'm interested in. But what's good, at least, is that that's the first chunk that was returned. And then, so the response, according to blah, 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 it gives me the answer. But there are other chunks. The other chunks also, in the Wikipedia page, sometimes they mention different numbers depending on like the dates, historical values, like is it inner city or is it with some of the suburbs, etc. So there are different numbers, and it seems this time it picked the one here, and it also mentioned the one in the like the urban area around Berlin as well. Okay, so that's one approach that I quite like. Another super interesting one is hypothetical questions. So we're going to look at this paragraph, but we're going to get the help of an LLM to suggest, okay, what questions could be answered by this paragraph. So the LLM will say, okay, when I look at this paragraph, oh, it speaks about Berlin, about the population of Berlin, the state where it's situated, etc. So the trick here will be that, as we mentioned much earlier, is the fact that query is the vector embedding of a query is close to the answer, the vector embedding of the answer. However, questions compared to other questions map even better, are more similar, and this is what we're using here. So we're going to embed the questions that are generated by the LLM, because we want to compare the query vector from the user with those questions. And of course, we embed those questions. But again, in the metadata, we'll keep track of the actual paragraph, and that's the actual paragraph that we'll give to the LLM. So that's what we do in this. I should have stayed in large mode. 37. That would be 30. Yeah, this one. Let's run it. So we're going to run that. Embedding store. Oh, yes. So that's the one where I'm using a StraDB. So I have a first part, which is here that ingests all the data in StraDB. So we load the document. We use Gemini to compute the questions. And the questions you will see here. So suggest 10 clear questions whose answer could be given by the user provided text. Don't use pronouns because, you know, Berlin, its population, etc. So we want to have the real nouns, etc., entities. And be explicit about the subjects and objects of the question, because we want a fully self-sustainable, can't find the adjective, self-standing kind of standalone sentence. And something I'm using, just a little trick. I want to retrieve the list of questions as a list of or array of strings. So I'm saying, okay, I want to have a structured output. So I can ask Gemini, okay, just return a JSON that has a list of sentences. So that's what I'm doing here.
Super useful in any Java-oriented apps.
As soon as you
are formatted at the output of the LLM, and sometimes you are just parsing manually.
Yeah. And then, so we embed all those pairs, all those questions, and we associate the metadata. I won't go too much there. And then the querying phase. So again, I'm doing a search. I'm going to say, okay, so here's, I'm using also a scoring model. We'll see that a bit later on. So what I want to show you is here. So the prompt template, you must answer the following question using that information. And well, the best I think is just to show you the output. So user question, how many inhabitants live in Berlin? So I've already loaded things in StraDB, and the similarity is 0.94, which is pretty good. And the question, how many inhabitants live in Berlin, match very, very well with the embedded question that the LLM computed and that we embedded. And if you look further, it looks like it's the same paragraph, because these other questions also matched pretty closely to the question. And I'm using ranking to see if one sentence is relevant, or one text is relevant to the other. So if one has got the answer of the question, basically, let's say that like this. And so it's several times the same output, because several of those questions matched very well with the actual query. And so so that's the request I send, and I just give once the very same, because it returned each time, interestingly, the same paragraph for different matching questions. Yes. And then it was able to use the first result and value that was given in the introduction of the document. So we've got a very high level of matching between the question and the hypothetical questions.
So here you are saving the different embeddings of each question and the paragraph. So meaning the paragraph is in multiple rows for each couple embedded question. And also this is where now in-memory store is not enough. You have this metadata that you need. And when you search, you will search with the similarity in between the embedding question and your question. But 2 questions with more likely to match. But what you actually put into the prompt is the paragraph.
Yes, correct. Another approach, so that's the one that was released or published like a couple of weeks ago, contextual retrieval. It's a bit similar, I would say, in a way, to some of those techniques we've seen. So, so that's the guys from the people from Anthropic who came up with this approach. So instead of storing this chunk, it's going to use an LLM to put or contextualize the chunk depending on the context of the document. So the idea is that, so similarly to hypothetical questions, we're going to use an LLM. The LLM, we're going to give it the whole document. Here is the chunk that we want to situate within the context of the whole document. And please give a short, succinct context, blah, 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 that situate the chunk in that document. So for example, for this particular green sentence, it's going to say, okay, that chunk put in context is about Berlin's population within its city limits in the largest, is the largest in the European Union. So it's interesting because here we're again embedding the context like we embedded the questions before. Here we're embedding this contextualized chunk. So it's not the exact chunk, it's not a question, but it's a chunk put in context. So we know it speaks about this. So when someone asks a question about the population of Berlin, there are high chances that it matches well. That said, so I can run it. Well, we don't have to run necessarily all of them. We're close to being at the break. Contextual retrieval. So let's close that. Let's run it. Okay. And so let's. I can start with the. Or maybe just look at this. So oh yeah, it's a. No, I thought. Yeah, we're not using sorry, we're not using Berlin this time. We're using a document which is about dimensionality reduction, like the different techniques that are used to when you've got 768 values, how to reduce that to a smaller space for visualization, etc. And I'm interested in a question which is, hey, what are the main dimensionality reduction techniques? And here we see the template that we mentioned. So try to put the chunk in context within that document. And when you run that, so I'm going to show you, so here are, so for this paragraph, we've got the contextualized chunk, etc. So we've got all the paragraphs. And when I ask the question, what are the main dimensionality reduction? You're going to see that, okay, this one matches well in terms of vector similarity. But if you look at the ranking, whoa, it's pretty low. That means that this chunk doesn't really contain the answer. Okay. Let's look at, so yeah, I forgot to mention that the first thing there, I think I'm doing the two, let's see what I have at the end. That's I forget what I wanted to say. But so it works well, but if you look at, so let me find it. Yeah, that's only I think it's the fourth vector. So it's not the most similar vector, but this one contains the actual responses I'm interested in because it matches at almost 1 in terms of ranking. And indeed, when we pass, so we create the model request, we pass the different snippets, and then it's able to give a good response with the right techniques that it found. And it adds some extra information from its own knowledge. So it works quite well, even if it doesn't necessarily give the best vectors first.
Mm-hmm.
at least in that example. It doesn't mean that it's necessarily always the case. And yeah, so we've seen the ingestion phase, calculating the embedding, searching
no semantic chunking. Okay.
Oh no, was there? Yeah.
You had the last
yeah,
one.
the last
semantic caching.
Yeah, semantic. Oh,
semantic.
Yeah. Thank you.
Which is
where's my? Oh, I don't have a slide for the semantic. Oh, strange. Yeah, that's semantic chunking, which is interesting because. So I'm going to show you. Oh, it's weird. Maybe I deleted it or something. Semantic chunking. Okay, let's run it, and then I think we'll do the break after that, right? Semantic chunking. So the idea is we're going to split by sentences. So I'm going to do that split here. But again, we're going to do some sliding windows. So we'll look at like 4 sentences, then one sentences. So we move one sentence by sentence, and we group by like 4 sentences together. And we're going to look at the similarity of those groups of sentences. And we're going to find, we're going to look at all those similarities, scores between them, and we'll find the one with the biggest disparities, with the biggest differences. And when the similarity is lower, we're going to rank the index or breakpoints where we could split by the lowest level of similarity. So we're going to group sentences, and we're going to decide where to split depending on how the similarity is. Is it good or is it bad? And we'll split where the similarity is the worst, because usually that means that the semantics of one part is quite different. It's like another topic maybe if the similarity is distinct. So that's, I won't maybe give too much detail about this, but I calculate the pairwise similarities between each groups of sentences. I then sort those similarities to find the lowest ones. And then I'm going to find the indices where I've got the lowest similarity between those groups of sentences. And I'm going to pick, I think this is, where do I pick the number? I pick like, I don't know, oh yeah, here. I pick like the 100, so that's back on the Berlin example, I think. I say I want to split up to 100 times, so depending on the length of the document, I might choose a different size. And then I'm going to find those indices, and then I'm going to regroup the groups of sentences split by the breakpoints where the semantic similarity is different. And then, so let's look at the outputs. So I found those indices, and for Berlin, so it grouped stuff about a bit of population and history, stuff which seems to be more about, well, there's a bit mixed stuff, war and so on. Here, lots of data. Here, oh yeah, that's the top ones, I think. So I didn't show you all the groupings because there's really a lot. But what's interesting is that it can group groups of sentences by meaning rather than like hierarchical fashion. Okay.
So this one is definitely slower because you need to split into blocks, compare each block one together, block that are very far ahead, split again, get the sentence, regroup by sentence with the same meaning, and that group will be a chunk.
Yeah.
So yeah.
And I forgot also some pros and cons of, for example, the previous one, contextual retrieval. It means that you have to send the whole document each time.
Yes.
That's costly if you've got big documents, and it's
I don't know. That's
slow
good
as well.
for you.
Yeah, it's
for
good
Google.
for my business, for my salary. But so there are pros and cons to those approaches, and maybe some of you have to try some of this. But for example, for me at least, I really like the ones where I have the sliding windows or the parent-child seem to work well on at least the kind of text on which I tried those approaches.
Okay,
so let's
time
do
for the break.
15 minutes. We're back at 3:15 or, yeah?
Yes. And yeah, it's just the ingestion. So you come back for the query after that.
Yeah, the querying phase. Welcome back.
Okay, welcome, welcome. Most are back, so we were not so bad in the first part, I guess.
Not so boring.
Okay, so let's close up with ingestion and move to query. A bit more than 1 hour to go. Okay, so we chunk with advanced technique. So we are not. We are kind of transforming the way the document is as input, even before translating into a vector. So now, let's say you do have your chunk, and you want to build a vector. How do you do that? Well, you call the embedding model, and you're good. But how does it work? Well, the embedding model has some token. So here you see on the side, inside an embedding model, you have an embedding matrix, and the row is all the vocabulary, meaning all the tokens possible in the language. Okay, and here you got the embedding dimension. So here we are keep talking about 768. That's the embedding dimension. Okay. So you arrive with your chunk. The first operation that is done is called tokenization. You, again, slice. We keep slicing things. You slice your chunk into tokens. Okay. As you see with the embedding matrix, each token is associated with a row number. So what we are doing is we are doing index mapping. We associated each token with its row. And with each row, using the inference model, we then have one vector for one token. And then we are doing an operation of pooling. Depending on the model, we are summing some average. We are doing some rescaling of those vectors. And you end up with one vector for the chunk. Okay, and this is what you save. So how do you choose your embedding model? Well, there is not one size fits all, unfortunately, but in the competition, and all the providers of embedding model build some benchmarks and some specific KPIs, and they are competing in these Hugging Face leaderboard. And it's a bit the same for different kind of model. So here, if I go here, I should load that leaderboard to see what it looks like. Hopefully.
Yeah, I had some issues with the Wi-Fi.
Okay, it's coming.
A bit slowly, but it's coming.
Yeah. Because here it's pretty good to understand. So here you say, oh, that's embedding model, and this is the parameter, the memory usage, the dimension, the max token, and so I will take the first one and I'm good to go. Well, actually no, because first you need to know what you are trying to do. Are you trying to do some classification, clusterization, re-ranking, retrieval? Okay, here we are doing RAG, so we probably want to do a retrieval. But is it enough? No, it's not, because then you have another dimension, which is here the language. Maybe this one, maybe you are working in French, and the NVIDIA one is not very good. And then if you look at the list, it's also now you need to check the memory. Do you want to work on small machine, commodity hardware, the dimension, and the token you want to work with. So it's not one size fits all, but at least here you get how models are classified and how they compete to each other. But don't trust those leaderboards too much, because now they train the model to be better at the leaderboard KPI, which is not all the time relevant to your use case. So my recommendation would be try multiple and do not try to stick to one. If I click, I'm back to full screen, right?
Yes.
Okay. So here the task requirements, the language, the domain specificity. So we had the question before, when do we fine-tune a model? Well, actually, the embedding model can be fine-tuned as well. And you want to do that, so first you will have to take an embedding model that's open source that you are allowed to fine-tune. And then what about fine-tuning? Well, you will fine-tune by adding your own token, your own keywords, if you are a specific domain. So maybe you will add rows.
Specific vocabulary.
Yeah, vocabulary. You add rows in your embedding matrix, or you change the coefficient for special type of query you want to do with existing token in the vocabulary. And you do that by asking a question, getting back the result, validating, so what we could labeling, what is the better, and that's you to change the coefficient question after question. So another question to ask is, can I fine-tune that model? Okay. What about the cost? If I cannot fine-tune, depending on the size, look at the cost. I think most people are looking at the cost, and you see that that's the only domain where the costs are divided by 2 every 6 months. So this one is pretty cool. Dimensionality, multimodal requirements is some model can work very well with text. It's written in the description, but some has been trained already with both text, image, or image and sound, and so in the same model, you have vector that will code both for image and text. So the most well-known was Clips, the open source, but now the big providers' model are mostly all multimodal and not multilingual. that I took my mistake, okay? And maybe you already have a stuck lock-in with an existing stack, so you need to take all the model on the shelf, okay? So
the multi-modal use case is interesting, for example, for e-commerce website where you've got pictures of your products and you want to also search for, you know, a coat, but maybe the description was vest or something. So you also want to be able to find the meaning in the images and match that in the search.
Oh, that's so lovely. You know, I'm a geek. Okay. I'm doing Magic the Gathering, and so I put the illustration of the card, and I say, give me a full deck with the same theme, with all the rest of the image.
Interesting.
So yeah, very useful day-to-day use case. So we told you about dimensionality. Lately, let's say this year, mostly this year, the embedding model on the shelf are trained in a way that the most meaning of the vector is encoded at the beginning. So here, if you look at here, I have a matrix. On the first column, this is where you find the most meaning. And so with the same model, you can actually say, I want to work with the full length of my vector. So, or I want to divide, so it's, everything is power of 2, okay? So divided by 2, here we divide 2. By the way, if you ask why 768 or 1536, you can say it's a power of 2, 2 to the power 10, plus 2 to the power 9.
Yeah.
And 768 is 2 to the power 9, 8 plus 2 to the power 9. This is why, actually, it's those numbers.
Thank you, math teacher.
I'm looking at you. I don't know, you know, right?
But yeah, models, for example, we've been using a lot the Vertex AI embedding model in those examples. And it's also a Matryoshka embedding model. So when you want to do fast vector searches, if you just look at the first part, basically, like the first 256.
And we did not come up with the name. It's actually the real name of the thing.
Yeah.
Okay, so yeah, sometimes just
fast
faster, so you get better latency and you lose into precision. So you will see that's also a lot of what you try to do with query. You are losing some precision for speed. Okay, so quickly, briefing. So in the embedding matrix, you remember that each token has a vector. This is how the embedding matrix works. Well, with a form of embeddings called Colbert embeddings, what you are actually saving is the vector for every single token of your document. and not only each chunk. And this is the Colbert algorithm that will actually compute the score for the for you at query time. So this time you are not saving the vector for a chunk, you are saving a vector for every token of the chunk. And so when you search, you will get all the token for your search query that will be compared with all the token for on the database. And it's at query time that the score is computed to get the similarity, and not just comparing two vectors anymore. You want to do that for the same reason you want to fine-tune your embedding model. You have a very dense data set with your special domain or your own acronym, and you want your token with a lot of meaning to be more present in the result. Embedding quantization. So this time we try to squeeze the embedding, not by doing dimension reduction with the Matroska or another technique like you were showing better with the retrieval context. Here we simply want to change the way the coefficients are saved. By default, it's a float. I mean, if you try a lot, you get float.
32.
Yes, but by using some quantization, and especially something called scalar quantization, you want to reduce the size of the model by degrading the signal in a way, going from float to into binary. You still get a similarity, and you still get the full pictures, but you lose some accuracy during the compression. So this is a lossy compression algorithm.
Yeah.
Loss compression.
But it's still Mona Lisa.
It is.
Even in black and white.
So when you see the all mini quantize, as we saw before, it's using some binary form of a coefficient, and this is why that still fit into your memory. Okay. Here it's really the scalar that are quantized, so it's not the vector, and we will see later how to use something called product quantization to get more meaning of the for the vector. Okay, so we got the document. We tried a lot of stuff to have high quality segment, and I just explained how to get those segments into embeddings. So once you get there, finally you will save that into the store, and so you save your text with the metadata, because you want to keep the source, the file name, the ingestion date, the paragraph if you use all your stuff, and all stuff that make your segment meaningful. And you will put the embeddings on the side, and you save that in a embedding store, also called a vector store or vector database in the world. So here you got document ingestion, last part, you have the segment, you have the embeddings, and you will save that into embedding store, and all those are supported by LangChain4j. Previously we mentioned AstraDB. It's a platform running Cassandra as a service by DataStax. So this is what we are using for our different demo. And with that, I think I should go into here and show here and see what I get here. So like before, we have some slides and we have some ready to go. Let me remove that. Samples for you to realize how it works. So for the slide where I get my chunk into token, into index mapping, into vector, here maybe I will not run it. This will be easier to read at the code. So here I have something using BERT, which is one way to tokenize. Those tokenizer also called sentence transformer. So you get the token. So that's a sample way. Yeah, sample way to do it. And here, actually, the Gemini tokenizer is available. You can download it. I don't know where you find that on Hugging Face,
on
maybe?
Hugging Face, yeah, or Kaggle as well. It's
okay,
available.
so you download the model. So you run the model here, and using DGL, which is deep learning
Java library, deep Java library.
Deep Java library, so deep learning for Java. You are actually able to load the model, and using this SP tokenizer and actually run that. So
what's interesting with the Gemini tokenizer and the Gemini model in general is that it's got a huge vocabulary of 256,000 tokens, which is twice as big as Llama 3 and 4 times bigger than GPT-4, I believe, which means that like some big words like integrating was just one token. And it means that you will pay for less tokens because you've got bigger tokens. So it's interesting also in terms of cost. So sometimes you see the pricing page of a model and well, maybe this one is cheaper or not. But then you realize that one has much fewer tokens and it's actually less costly than the other.
Yes.
Just for the side story behind that.
Go. Thank you, teacher. Okay, multilingual, we did it. For retrieval task, so here we wanted to show you a new parameter that has been introduced at some form of model like Gemini. And the line is really this one, where you actually question your embedding model. You can actually tweak it to a certain retrieval type.
Particular task. So you say, okay, I want to embed this because that's the document I'm going to embed. But then you've got at the bottom retrieval query. It's a different task. So it's embedded slightly differently, but compares to the retrieval document embeddings. So it gives better results, better matching. Well, it gives a result. It's not very meaningful, but and for example, that Vertex AI embedding model, there's the last version added a code retrieval or code query. I forget the exact task name. So, for example, you can also embed pieces of code, and let's say I search for an algorithm that does this or that, and it's able to compare the sentence, the query vector with. You can imagine that code is probably encoded much more differently, but there's a dedicated task to search for code. So you've got better similarity results for those kind of tasks. So look for models that also have particular tasks support.
Speaking of item in the model, in the case again of Gemini, so Gemini and the text embedding 004, which is the latest, is a Matroska embedding. So here is how you define the dimension you want to work with. This is here the output dimensionality. So again, Longchain 4G is there interacting with APIs, at least for Gemini. So it's just a new parameter in the API that has been translated into the builder for the model.
But ultimately, like the 256, that's really just you cut and you take just the 256 values, and they are exactly the same as the beginning of the bigger vector.
Okay, so
and there's there's an assertion that checks that.
What are you logging here? Oh, you just show me the vector.
I show the vector, but at the end I ensure that they are the same.
Yeah, that's you still get. Oh, it's true. Okay, yeah, nice output. So it works.
It works.
No, so what you try to say is that okay, the sublist is equal to the big one.
Yes.
Okay, thank you. So
let's move on.
You prove to the trunking. Okay. So now let's talk about those database, because we know we need to save all those. So this is the database part. How do you build a vector database? What are the constraints for the vector database? So first, you need to save and store vector. So you need to have a way to represent a vector, save vector. And the second is later on, you need to be able through queries to do semantic search. Okay, that's what we just talking. But it's not only type of search. You want to search also on metadata, key value. What about the existing search? Why it's only on vector? You will have to search on metadata and other stuff. You also will have to search on maybe others form of meaning or connection in between the document, not only the similarity. So, but first, let's look at the similarity. So the demo we did was on AstraDB using Cassandra. And so what happened last year is Apache Cassandra, NoSQL database used quite a lot, even with pretty big cluster, has been translated into a vector database. Okay, so that's a slide from ApacheCon 2 years ago, where Apple well stated that they are using 300,000 node in production, which is not too big. So in Cassandra, it's a distributed database. You can have as many nodes as you want. It's scaled linearly. On one node, you have 1 terabyte of data. Okay. They all communicate to each other, and the data is replicated. So you can lose any of the node, and it's still working.
And if you lose all the nodes?
Well, you have bigger problem.
Probably.
Actually, in a single Cassandra cluster, you can have multiple rings. And so you will have one ring in one region, one ring in another region. So even if Google region is going down, you're good to go. Okay, so at least what Cassandra goal try to achieve is really always on. Data is replicated, you can lose any node. Linear scalability, you need more power. You simply add new nodes working on commodity hardwares. Low latency, that's the way you ask for a query. The client itself will encode your query, get a partition, and as is aware of the cluster, will actually ask for the proper nodes that have this particular data. It's global distributed. Those nodes can be everywhere. So that's our starting point. This Cassandra, for Cassandra 5, has evolved into a vector database. So what has been done is you need a new type called vector that will take a vector of something and the dimensionality. So here also dimension for short, at least in the Cassandra field. So here you see in an existing table, we simply add a new column called item vector of type vector float 5. Okay, it's not a list because it's a fixed length. It's not a tuple. It's not a map. It's really that thing that needs to be introduced.
Multi-valued.
Exactly. So, but you
Floats.
don't need to be a vector database pure player. You just have all the cool stuff, and you add the vector capability. When you do a vector, you need a vector index, how all your data are saved on disk to be able later to perform similarity search, vector search. And we will go deeper with that before end of this session. So here you need to create a new form of index, which is a type of index to search on vector. Okay, so second type of things to be added. Last, we had to change the language. So if you're also using some other type of databases, relational, PG, Mongo, Neo, they all changed the language to attach this new capability of vector search. It's not something magical. It's something that has been added to most databases now. You can check. It's not a clause. It's not a where clause. It's a order by, because you want to get the vector that are the closer to the embeddings of your question. So it's simply an order by. But that's keep offering the possibility to add where clause with your existing data, your existing metadata filtering. So your existing column to do some metadata filtering. So the idea when you save a chunk in the table, in the store, you will also have the source, the ingestion date, the format, the type of file. Because what you are ingesting are files that are not static. These styles will live over time. So, and everybody told you about ingesting the document once, but if the document has changed, what do you do when you ingest V2? What do you do with the existing vector store? Well, if you do not have a metadata to encode the source, well, you cannot do, remove everything related to that source and embed it again because that's changed. Or if you don't want to re-embed the full document, you can actually recompute the chunking and look at the database if it's already, the chunking is already there. And if it's already there, I don't need to encode anymore. And how do you check that an embedding is not already there? That's also using metadata. So the metadata could be like MD5, hashing of the chunk. if the hashing is already there, I don't need to reingest again. And all of a sudden, you win a lot of money now because you don't have to reingest everything each time. All this ingestion will happen over and over again. So you need to find a way and some keys in your database to know that it's already there and not redo the work another time. Okay. So with that, we finally...
Just another filtering, like mentioning you want to search stuff that is geographically fenced, like I want to search about all the monuments in Antwerp, but not all monuments in the world.
Yep.
Or
So
customer data, I just want to search documents for that customer.
So for the
filtering is super important.
Yeah, for the geo type search, you have a dedicated geo type of index, or you can reuse existing index for geo search. You think about facet into a Lucene or special type into Elasticsearch. You can reuse those search alongside this new search. And so here we will talk you about the query and which type of search comes first and how do you combine results from two different type of search. Okay, and I will do the sample code after that. Okay, just so here are query processing. So that's another way of showing you the naive RAG. And here now we're zooming into this processing the query. So Long4j, Longchain4j gives you these abstract classes, content retriever that we found in the naive RAG, that will get you a builder or a syntax pretty simple enough for you to just define the model, chunking strategy, store, click the button, it's okay. But as you can see, as we now introduce new way of chunking, new way of searching, new way of saving, it's good, but it's not good enough for us to do what we want to do with advanced RAG. So this is why we're going a bit aside Longchain4j or beyond. Okay, so here before this, let's see what we got here on the vector database type of query. Okay, so here we're not there yet. We go here. So the content retriever. So that's this little guy that gives you everything you need. So here I'm loading a text and I can use the content retriever and start interacting with the model. But everything is by default designed very, very simple. If you look at the retriever, I got my store, I got my model. I can fine-tune a little bit, like how much data I want, how much results, and the minimal similarity. Their score is not a good term. The minimal similarity would be better. So it's doing that for you. That's great. But what if we want to go a bit beyond that? So let me go before that. I will probably
start the test.
Yeah, just thinking if I no, let's go. Okay, let's go with the order. Okay, so okay. Now let's go with the query mode. And the query mode, first you get that content retriever doing the basics. And we will try to get a bit more than that. So now what if you have multiple source? If you have multiple file, or if you have secure stuff, not secure stuff, or if you want to search multiple store, I would do that. Well, you will have probably one retriever for each source. That's still okay. But what do you do in front of it to do the routing? So in Longchain4j, they introduced the concept of query router, where you define the list of content retriever and rules to know which one to pick. So you can also have some a very big file or very big data set and a tiny one, and you want the result to be balanced, so you can put some weight in the inputs. This is what LangChain4j is capable right now. So here I have content retriever using web engine. Okay, so you can enrich your RAG not only with data from the file or of the vector store, but also from the web search. Here you can simply say, I want my query router to look into my content retriever web, and also in my content retriever this file. What it will do is here do RAG fusion, and it's a bit and the fusion this time is very naive again, because it will do side by side, and you will get the chunk which is the concatenation of both, without any weighting, without any. It's just the same amount of chunk in both.
And the LLM will be responsible for figuring out which one of those
which
segments
coming from what,
the
right?
most interesting for answering.
And it's not it's not first go into my document and they do a web search. They're just going both at the same time and get the concatenation. So that's one way to do it. Okay, and actually, those operations are done in something called the Retrieval Augmented. So that's the biggest object where you can start doing what they call advanced RAG, and query router is really just the first part. If you want to build your own custom routing, they get you that my router over there. So what I did in this sample is I do have two files, one talking about dog, one talking about a horse, the same as before. And I say, if the query contains horse, look at this file. If the query contains this, look at the other file, and it will pick the proper store based on that term in the query. Of course, it's a fake it sample. But what now if you do the same with the credentials, the permission, and the role of a user? Oh, now all of a sudden, an administrator will be able to look for different store with different level permission that others could not do. You build your own role-based access router if you want.
Or you could use an embedding model to compare or do text classification, figure out this query is more about this topic than the other. There are many ways.
You pay by the token, right? You are paid by the token.
I should have that on my t-shirt. I'm paid by the token. Use my large language window, context window.
Yeah, that's totally what you do. Yeah, okay, so if you find the horse, you find the dog names, that's a sample for this type of routing. Okay, that's the first item of graph RAG, which is this router. Second one is I want to transform the query. So we transform quite a bit the chunks, but now we want also to transform the questions. And one thing that could happen is you are doing some chat, and you have a lot of different query, answer, query, answer, query, answer. And if you put back every answer, question and answer each time to the LLM, it would be super happy, but that will be a lot of token again. So instead of doing that, what you want to do is compress the query and just get a query that is shorter. So here we do have a query compression sample where in the retrieval we simply say query transformer. Okay, so now look, check the query compressing transformer. Actually, it's summarized using a LLM, but at least you do it once to have a shorter content and get the result. This time, the output, sometimes our little sample on Berlin got not enough information, and when we compress it, sometimes it's stating that I was not able to find about that particular solution.
But one example would be like you have a first question, hey, what's the capital of Germany? And it says, oh, it's Berlin. But then you ask, what is its population? And when you search for what's the population, doesn't know it's about Berlin. But if you do query compression, then you're going to have what is the population of Berlin instead of not meaningless, but incomplete question.
Yeah, so here this time I bet is used on Google because look at Precise is the guy.
Oh yeah, maybe.
Okay, content ingestion is another technique where you transform your request by injecting a prompt, by injecting more data. So here it's a sample of here content injection where I set my prompt template, I set my metadata. I try to keep moving with those query compression and samples. Okay, so all that are router and transformer. What if now you also want to change the query, but with the LLM getting a better or richer query?
Yeah.
And here you have this pattern too.
So you remember the hypothetical question approach where we embedded questions about the paragraph, right? So it's similar, but it's, let's say, on the other side of the fence in the sense that here we're going to do something similar, but on the query level. So here, still the same question about Berlin, but the user query is, what is the population of Berlin? But instead, what we do is we provide not a question, but a fake answer. Maybe the LLM is not that smart and doesn't know much about the population. Maybe it's going to say, oh, there are 3 million inhabitants in Berlin. It's a wrong answer. Okay. But if you search and you embed that query and you compare the vector embedding of that hypothetical answer with what's already embedded in the vector database, the matching, the similarity will be better. So let's open, what is it called? Hypothetical document embedding. So I'm going to run it and I will explain what you see. So this time, yeah, that's I'm back to dimensionality reduction. I could have stayed with, I guess I need to run this guy instead for having the right environment variable set. Yes. So I've got my dimensionality reduction document. I'm going to split by paragraph, and I'm going to ingest that. So it's the normal naive ingestion process. Okay. Then we've got a question, which is, so the question is here, what are the main dimensionality reduction techniques? And what I'm going to do is, hey, LLM, please provide a short and concise answer to the user question. So it could be a very small LLM that's not very knowledgeable, and it would generate some kind of hypothetical answer. And we're going to compare that hypothetical answer in when we do the search. So I'm going to do two things here. I'm going to search with the original question. So what's the what are the dimensionality reduction techniques? And next, I'm going to do another search, but with the hypothetical answer. I'm going to match that, and you'll see. So it should have run. So question is here. This is a hypothetical answer, which seems to give the right response already without even doing RAG, which is good. So if I do the search with the original query, okay, first result 0.9. It doesn't contain the reduction dimensionality algorithm. Second one, still good result, still not containing the right information. And it's only the fourth most similar vector with a lower score that gives me so PCA, TSNE, etc. And that's the information I was looking for. So that's with the original question, not with a hypothetical answer. Now I'm going to do the same thing with my comparing and doing the search with my I struggle to say hypothetical answer. And look, the first result returned with the highest level of similarity. That's now indeed the right paragraph that contained the dimensionality reduction techniques. So that's interesting to see that it, at least on that example document, it works. I'm able to get better vector results than not using that technique. Right. Okay. And I embed the same thing as usual.
But I'm now wondering if during the ingestion you are doing hypothetical question replacing by answer, but it answer you respond by hypothetical question.
But you can combine those techniques together.
Okay.
And I'm doing hypothetical talks at hypothetical conferences as well.
Wow.
Sometimes. I'm a hypothetical expert in AI, as you noticed. Maybe.
Oh, wow. Okay, back to our database business.
Yeah, I'm paid by the token, you paid by the row, right? In the database?
Yeah.
Right? Okay.
Give me big chunk.
Sure. Lots of them.
Okay, a lot of queries would be better. Okay, so actually the database is supposed to do all this kind of search, actually. And so if you want to build a vector database, this is the problem you need to face. So same as for the embeddings model, there are some dashboards and comparison comparison table. Here it's superlink.com, where you see the vector database and the different capability expected. Okay, if it's multimodal, multi-vector, geo-search, face set, hybrid search. So hybrid search is really be able to address two types of search and be able to give you a single set of results. And we have a demo for that. Okay, so now let's say you want to build a database, a vector database. You have a set of vector. You save them as is in a table. And you want to do some kind of search. What will happen if you do this type of search? Yes. All right. So you start to ask every single. You try to find the numbers. And so if you try looking at every single vector and compute the similarity,
with all of them,
it will take forever. So it's not a good approach. So first things you need to do is divide for conquer. So your vector space will be partitioned, and the partition is done using KNN. So k-min. So the partition is done using k-min. Okay, yeah. And so you get each partition, and in each partition you will define. You will find the center of the partition, and this is the centroid. Okay, so you do that with your vector space. Then when you search, KNN is just too slow. You need to do some approximation. You need to do some approximate nearest number algorithms. Different algorithms. It's even probably too small for you to read. Oh, not here. You can see all of them. But here, this is what the vector database provider compare against. So it starts here. With not a lot of query per second. So the recall, you want it to be 1. So the recall is the number of relevant item retrieved divided by the total number of relevant item. So did you find all the items that you were supposed to find? So small workload or small data set, everything's okay. But the more throughput you put, or the bigger the data set, you are shifting to the left, and you try to stay as much longer as long as you can close to 1. So that's the recall, and every benchmark we do when we assess the vector database performance is first the recall. Okay, so to be able to do a vector search ANN, there are multiple family of index. So when you save all the vector, it's index, different type of index, hash-based, tree-based, cluster-based, graph-based indexing. So most vector databases are using the latest, which is a graph-based indexing. So all your vector and similarity, so the vector are the node of the graph, the similarities are the edge of the graph, and you compute the similarities when you save, not when you search. Because then when you search, you already know which are your numbers. So it's not graph RAG, it's just how vector database works for now. Okay, so different way to build those index, and the most used, like 1 year ago, was this hierarchical navigable small world where you have multiple layers with decreased radius, and you start with the highest level, level 2, and you find a vector, and then you dig one layer, you find the nearest neighbor, or at least the closer one. You dig a layer, you find the nearest number. If it's not good enough, you go back, you search another one, and see it's an algorithm when you go into the layer and you try again to split your graph in multiple layers to make it faster. But to be honest, it was so 2023. So now most have shifted.
2024. Come on.
we shift to another form of vector search, which is NNL. First, we try that on Cassandra, and Cassandra we try with 1 billion vector to start with. It's Cassandra, and we blew up. So that algorithm memory is not very good. So we checked at different algorithm and solution, and we found out a paper by Microsoft that was disk ANN, where you build a graph using one particular algorithm, and you do a little some optimization to be able to get a very performant vector index and vector search. So it's called gvector. It's open source. It's also a full Java vector search engine. So it's using some disk ANN, so it's a paper where you build a graph as a single layer using something called the Vamana algorithm, where you start to position the node on the node on the graph, and you still doing the similarity, but you are not computing the similarity. You try to make sure that so you set a radius. And for each similarity, the algorithm tried to get the edges as far as possible one to each other, but it's getting denser and denser to get up to something like that. Okay, single layer, denser collection. And so the recall, it's better because you don't need to dig into the layer and go back. So you're most likely to get all the matching document and not losing one document into the layer. A second approach, we need to compress. So it's a way to quantize, but it's not scalar quantization, it's product quantization. The vector itself, it's quantized. So we start with the original vector. We split the vector into pieces. So here I take 4. You get a subspace. And then you do Kamin again, but in the subspace. So you get this type of Voronoi diagram. And so again, you put back what I explained before, the centroid. So to each subvector, you find it which partition of the Voronoi space it is, and you associate the centroid, which is the center of that partition. So 1024, 256. Here you got one double, so 8 immediately. And so here, once you got there, you simply concatenate those centroid IDs to get the output vector. And so by doing that, you compress the vector. Actually, once you get there, in gvector, it's going one step further. It's even compressing that vector into binary quantization. Okay, so here, efficiency, speed, and scalability, what we try to achieve with gvector. Moving on. And so this is another tip and tricks when you navigate the disk ANN graph. You search on disk, and so to reduce the I/O, you want to limit the read count, so you oversampling when you read to avoid jumping into the graph. Okay, with that, so Lucene already had, for years a way to build this type of graph index using HSNW, and now with gvector, this is what you get. Okay? So another, and here don't look at the matrix, but here measuring the success of RAG, I already explained and showed the formula twice about the recall, which is the number of items you retrieve and how you were supposed to retrieve. You want that to be 1. What about the precision? The number of relevant item retrieved by the total item retrieved. Sometimes you get more than what you were supposed to do. And so again, to do the rescaling and the rebase, we are computing something called F1, which is the formula here. So when we do some benchmark of those databases, we check the recall, the precision F1. And when you are doing RAG, after all, this is also the type of metric you check if your RAG is good enough. So moving on, this is what gvector is doing. And I'll take quite a few time because it's open source available to be used. Okay, so we're super happy about it. And now thanks to that, we are super well rated. So now that we did the search, now what about what can we do after the search to make it better? Okay. So here, different algorithm, and first is reranking function. So first you got the similarity in between vector, and they are ranked decreasing by similarity. Is it good enough? You demonstrate in your chunking technique that by re-ranking, you get better results. So you need a re-ranking function, which is different from similarity search. And so different ranking function. Those ranking function and way to implement that in Longchain4j, it's through the content aggregator. And we need re-ranking function, so scoring model. The scoring model will give you a score, and we will re-rank by that score. And so if we look sorry, at the samples we do have over here ready for you. Okay, so here we go. It's decreased order over here. So category compression. Okay, re-ranking. So you got a scoring model to get you the re-ranking. So here scoring model. The default use is Cohere, because Cohere one of the first provider to provide this re-ranking function. And so you use the content aggregator and the retrieval augmentator as before. And here you simply define the scoring model function for the content aggregation. And so it will re-rank, reorganize your chunks. But because we wanted to push a little bit, we say, Cohere and the default function, it's not good enough. And so we implemented the BM25 ranking function. So to be contributed very soon to Longchain4j. But here in the code, we actually re-implemented the BM25, which is looking at frequency of terms in the...
It's a standard keyword search kind of algorithm, let's say.
Yes. TF, IDF type of search. So frequency of word.
And we're going to combine both.
Yes.
To get the best results.
Exactly. So this is a first re-ranker we had there with the sample code. And then we went, okay, can we do even better? And so here we have the another scoring model, another function, which now is RRF for reciprocal ranking fusion. So you have one particular order, which is your similarity search. You get another type of search with another type of document with another, it could be BM25 or another search. And here we are merging the two lists in the single order list of item with the RRM algorithms. So it's there as well to be executed.
So you'll be able to study the code more in details.
Yeah, we're looking at we're
clock
jumping
is
because we're jumping because we see the clock over there. Okay.
But it will be also better once it's integrated in LangChain4j, because we had to implement some of this.
Yeah, like all the chunking techniques, all the re-ranking
Yeah.
techniques will be contributed back to LangChain4j after that. So the re-ranking RRF needed not a list of results, but a list of results. So I'm also getting out of the default signature and was not able to use LangChain4j to do that. But the idea is, simply using that formula and this ranking to re-rank as a bigger list with those two. It's as simple as this formula. Really applying the formula better, just like this. Okay. Finally, we get to the graph RAG. So in the database, we and the vector index, you do have. It's already stored as a graph, but each node of the graph is a chunk or vector related by a semantic similarities. And what you're doing when you do a semantic search is looking for the nearest number, looking at those edges more or less. What about graph now? What can graph bring into the mix? So the notion of building a knowledge graph, now the subject are nodes related to object by a relation or a predicate. So when you search those graphs, you can either do a traversal. So let's say you find the subject you are interested in, and then by navigating the predicate, you find more stuff that get you interested. But so you can combine both, right? You can have the subject to actually be a chunk. So you look at all the subject that you're interested by using a similarity search with all the chunk, and then you navigate the predicate to get what you're interested in. That's one way to do it. Another way is actually to save your graph as a list of triplets. And the triplets is your relation. Subject, predicate, object. And this is actually what you save in your table, regular table. And there you do also some embeddings of that triplet. Because why now? Why not? You have a database that is optimized for all this vector search. Why not encoding these highest function knowledge as also this type of table and encode as a vector? So to build a graph RAG, you need to build the graph. So you need some kind of engine, for instance, HTML that will crawl the HTML website and relate the document by HTML link. Or you can relate the document by a keyword with the keybird algorithm, or content-based entities like you did content-based retrieval, this time using Linliner. Those algorithms are not yet coded into LangChain4j. They are in LangChain. So what we keep doing is integrating those goodies into the Java language. But once you get the graph, then doing the query, you can either compute the embeddings and navigate the graph by triplet embeddings findings, or by building a graph traversal. So of course you will hear like graph database provider or vendor that will use the graph traversal. So you can graph traversal the existing graph, but there is absolutely no need for a graph database to do graph RAG. You will simply encode the triplet as a new form as embedding. And this is actually what we did in the Cassandra Graph Store, where you have two tables, one coding for the nodes, with the embeddings, traditional vector search, and another one coding for the graph link, which is the second table, graph target, where you find an embeddings again for the link, and everything you need to do the search. And with that two tables, you can search only for the node, or for the node using vector search, and then using the graph target to go one step deeper, find other nodes, and like that you can navigate your pseudo graph without any graph database actually. Yeah, we give the slide, and the notebook collab is there for you to run that sample as well.
It's Python.
Yeah, this is why I don't show the demo, right?
Cool.
Okay, right.
Yeah, thank you. Something I wanted to cover as well is agents, function calling, and agentic RAG. So you might be familiar with function calling. That's the ability for an LLM to say, okay, I need some more help because I don't know the answer to something. And maybe if I had access to an API, a REST service, etc., maybe I could answer that question. So let's say this little user has a question about the weather in Paris. Well, the LLM doesn't have that information because that's real-time kind of information, so it's not part of its knowledge. So the chatbot app is going to send the query, but in addition, the chatbot app will tell the model, Gemini or something else, by the way, there's a method called getWeather, which takes a location string that can be called. And it's up to the model to decide, oh, actually, since I don't know anything about weather, I could be useful if we could call that function. And the green arrows are things that are not visible to the user, so that's very internal. The model will reply with, hey, if you could call getWeather with Paris for me, please, I could give you the answer to the user. So your chatbot app, and LangChain4j takes care of doing that automatic function calling for you. The chatbot app is going to call the external service, retrieve the results. Oh, it's sunny in Paris. And then you give back the JSON response of that service to the LLM. And the LLM, oh, now I know, it's sunny in Paris, and then the chatbot app can transfer back the response to the user. So that's function calling. And why do I speak about function calling? Because it's used in AI agents. So there are different types and capabilities for agents. One aspect is reflection. So things like chain of thought, how to think step by step, etc., or sometimes they call that or self-RAG as well, self-grading, etc. Like it gives you something back, but then the app replies with, yeah, it looks okay, but it seems there are some errors. Then the LLM can fix things that's useful for coding, etc., for example. So that's self-reflection and chain of thought kind of decision-making. Then there's the planning phase, where either when you are implementing the agent, you're very prescriptive, and you say, hey, you should follow these steps, or potentially the LLM could figure out the steps to follow, and then the functions to call on its own, different approaches. And tool use, because that's the mechanism for an agent to go beyond what an LLM is able to do. And then you can also combine things together, because a function call could be calling another LLM. And when you combine things together, you have an agent. So I have an example for that, which is, so I'm back to the example with the Berlin page, where a user is interested in Berlin's, like its origin, its population, its geographic situation, or maybe something else. So you define several topics. If you want to do that with RAG, you would have to kind of manually do several searches to do that, and then maybe ask the LLM, okay, now make a summary of this, or so you'd have to prompt the LLM manually somehow to do that. But here I'm defining an assistant, an agentic assistant. I'm explicit about the steps, at least in my example. So I say, hey, identify the key topics asked by the user, create questions. I'm going to reuse my hypothetical questions embedding, which I stored in AstraDB. And I'm going to do the RAG search for each of those questions, for each of those topics. And then this top-level kind of agent will be responsible for collecting the answers and generating the final report. But in the meantime, for each topic, it's going to use a tool that's going to do the RAG searches for each questions for each topic. We do the RAG search, we retrieve the results, and then I've got another assistant, so that's really two LLMs talking together or working in collaboration, studying the topic and the answers, creating a summary of what was found, returning a report for just like the origin or just the population, and then by combining everything together, the main agentic LLM assistant will be able to reply to the user. So here I've got this example running Agentic RAG. What was it called?
49.
40.
Okay, where is it?
Where is it? Where am I?
No, UI experiment.
Oh, sorry. Yeah. 49 is here, so I don't need that. 49, and this is what I coded there, which is, okay, I'm going to define the master, the main assistant. So I could change the query. So I'm going to run it as well at the same time to see the results. That's not this one. Okay, run, because it takes a bit of time. Okay, let's run that. And while it runs, I continue my explanations. And so here's the contract I have with the system message. Okay, you're a helpful history, geography assistant. Here are the planning phases, the planning steps I want you to follow. Identify the topics, prepare questions, query the database, collect the answers. But when I create my assistant, you see that I pass a tool, and that's how with LangChain4j you can define a tool with some special annotations. Okay, here it's search information in the database, and that's where I'm going to do the RAG query. And in that RAG tool part, I'm going to use the second LLM assistant I mentioned with the usual RAG approach, naive approach, although I'm using hypothetical questions. And then I'm going to return the results. So let's see what it looks in output. And you will see, okay, for each question, I'm going to find some sources which contain the information. I'm going to create a first report for the population. Same thing for the other things. I'm going to do another report with my findings, and then I can combine and create a final report. So it's an advanced use case for when LLMs and RAG is a great approach, but for more generic kind of use cases with broader scope, it might be trickier to do, and maybe Agentic RAG can help go beyond the question-answer approach.
But it's great to see
Not much time, but
it's already there.
It's already there. So you have to evaluate what you're doing. There's a project, Python again, called RAGAS, which suggests some metrics at generation time or at retrieval time. There's another interesting project called DeepEval, again in Python. We're a bit lagging behind.
But for the talk,
we implemented
a bunch of functions. So you already learn about precision and recall. And if you go next, there are also two others KPI called MRR and NDCG that we cannot really detail. So you compute and you have your similarity, your score for re-ranking, and you have these KPI. And so if you try multiple embedding model, multiple approach, you can compare how good or bad those metrics evolve based on what you're doing. So at least we implemented those two. So
you'll have to have a look at those examples. There's another approach which is also about using an LLM to gauge the quality of the answers. Sometimes it's called the LLM as judge. Judge dread, that's the dread of evaluation, Anyway, there's OWASP mentioned various problems with LLM applications in terms of security, but that also applies not just to just using an LLM, but also to the RAG approach. A few other things you might want to consider, like anonymizing the data, and especially when you're logging stuff, maybe you want to redact some important PII information. you may want for data privacy reasons or also laws local to your country to use
PDC.
GDPR, etc., to run locally or on your own server or in your own region. So you can also think about that. Here we used model like Gemini, which also runs in Europe, but
But that's also why we recommend to use this RAG approach, where you have all the data locally, and what you send to the LLM, whatever the LLM, locally it's better, but even if it's out there, you send your question and really just the extract. Whereas if you're using something that they call the assistant API on the LLM, well, you need to give them everything and
the keys to the kingdom.
And keys to the kingdom,
And we covered that a little bit when you mentioned the metadata. If you use a vector database especially, it's important to have good level of metadata and metadata filtering because your data is going to evolve. A new version of the document is there. You need to remove the old vectors and re-embed the new vectors. Maybe you mentioned caching, etc. So you have to think about that. The data lifecycle is important, and your data is staying alive. I've always wanted to do that on stage. And think about like a cron, some kind of schedule. When do you want to check that the data is stale or whether it needs to be updated or not? Conclusion. So there's not one size fits all solution. You'll have to check with your own data whether one approach, like an ingestion approach, works best or not with the density of information. You'll have to see what are your constraints in terms of like the multi-tenant kind of apps, depending on your country regulation. So there are lots of things to keep in mind, and also you mentioned the leaderboards where you can also compare when something...
I think at each step of the pipeline, you have the question to ask and different samples, and you also know how to evaluate if it's good or not. So now it's
and you have to and you have to think also about the kind of questions your users are going to ask, how you integrate things. So simple questions like yes or no, or looking up some data is okay, but stuff where like a multi-hop kind of questions where you have to search some information in the doc, then in another, etc., will work less well with a RAG approach. So maybe an agentic RAG approach might do better.
Or graph RAG.
Or graph RAG as well, which should do well in that kind of scenario. So think about the kind of queries you'll get. And ultimately, you can also combine a good database with an LLM that has, I'm paid by the token. So a large context window is interesting because when you want, let's say, to ask a questions like, compare the different trajectories of those countries in the economic blah, 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 RAG can look up precise information, but it's not able to reason on large documents. So you may have to look up a couple documents and ask the LLM with its big context window to make the actual reasoning and thinking and deduction about the actual contents. And that's about it. So there's this book from Antonio if you want to get started with LangChain4j. And all the code, again, is available here. You can scan this QR code. So thanks a lot for your attention. Thank you.
And if we get even beyond.
Because attention is all you need for those
Bert model
who've read the paper. Thank you.
Thank you.
All systems are nominal. Initialize Genesis sequence.